Yeah. So we see in this frequency divided circuit in the digital we already seen. So here we see in the circuit that is divided by two circuit. So divided by two circuit means there is a one clock cycle, but when you are getting this for the Q, you are getting time is doubling. So frequency is divided by two now. I explained this circuit. Q bar is connected as a feedback to D, and this is a master clock. And so first I explained this frequency divider circuit. Did you remember? Okay. So for this, I'm going to see the code frequency divided by 2 circuit. Uh, so here, if you see the circuit, you see the program RTL code. Module frequency divided by 2, input clock underscore in, input reset, output reg clock underscore out. So always at the rate passage of clock or passage of reset begin if reset. Okay. Clock underscore out. So clock underscore out equal to what? 0. Else begin. I need to toggle. That means clock underscore out equal to what? Not of clock underscore out. Is it fine? Okay. So this is my code, and coming to the test bench. Test bench is same only. Like five steps we need to follow. First, we need to declare the internal variables, clock in and reset with reg data type, and clock out with y data type. You need to instantiate your design in the test bench, connection by name, generate the clock, okay, generate the clock, connection by name. So always hash by clock equal to not of clock. Clock underscore in equal to 0. Reset I am applying. After 15 time units, I am releasing the reset. I am audible, no? Yeah, yeah. So after 100 time units, I need to check dollar display and dollar finish to finish the simulation. Dollar monitor is to see in the TCL console. This is the test page. Is it fine? Okay, and I will share this code. Sir. And next we discussed about this. Our agenda is we need to design frequency divided by f by n, where n is odd and when n is even. Okay. First we discussed about n is odd. Okay. So n is odd means we are using mod 3 counter, but we are not getting the 50% duty cycle. We are getting 33.33% duty cycle. So what is the like what is change we need? So we alter the output frequency by 1.5 cycle, 0.5 cycles. For that, I am using negate of D flip flop, no negative edge trigger D flip flop. Okay. So by designing this like this circuit, Q2 and Q1 are Q1 and Q2 are connected to OR gate. So that I will get the frequency divided by 3 circuit with 50% duty cycle. Okay. So for this, I can write the code uh, frequency divided by 3 circuit. This is odd number. Yeah. So this is odd number. Frequency divided by 3 with 50% duty cycle. Okay. So if you see the design, module divided by 3, 50 DC, input clock, input reset, output Y. I am declaring one count that is 1 down to 0. So frequency divided by 3 means I need to design mod 3 counter, no? How many flip flops are required? How many flip flops are required? 4 flip flops are required. No? 4 flip flops are required. 1 second. 2 flip flops are required and mod 3 counter. Okay, 2 flip flops are required. Okay, so that's why I'm designing count with what 1 down to 0. So reg Q1 and reg Q2 mod 3 counter. Okay, I'm designing mod 3 counter. It should count from 0, 1, 2 up to so on, and again it will come roll over to 0. Okay, always at the rate passage of clock or passage of reset begin if reset. If reset equal to 1, I'm initializing count to 0 and Q1 to 0. And else begin. If count becomes 1 0 also, it roll over to 0. Okay. Else count equal to count plus 1 tick binary 1. Okay. Just I am designing the synchronous counter only here. Okay. After that, I am designing that is a negative edge trigger D flip flop. I am designing. So that means always at rate negate of clock or passage of reset begin if reset. So Q2 and initializes to 0, else Q2 equal to Q1. Okay. So what is the final stage? Q1 and Q2 are connected to OR gate. Yeah, OR gate. Assign. Okay, and I'm giving assign. So I'm not declared with red data. I declared with white data. That's why in the I'm using continuous assignment statement assign y equal to Q1 or Q2 and end module. Okay. This is divided by 3 circuit. Okay. Shall I tell test bench or not required? Same only. Yeah. 5 steps only we need to follow. Okay. So 5 steps we need to generate the you need to initialize the internal variables, generate instantiate your design, generate the clock and apply the stimulus. Okay. So this is the test bench. And next we have seen F by 5 circuit, no? F by 5 circuit with 50% duty cycle. First I designed modify counter, and if I see here, if I see Q2, I need to use two flip flops. One is passage of D flip flop and negate of D flip flop. Why? Why? Because I need to alter the output frequency by 1.5 now. So I need to optimize that circuit. So in order to use Q2, I am using which one? Q1. Okay. So we discussed in the digital. Okay. So if I use Q1, I can alter the output frequency by zero point 0.5 only, so that I can use one negative edge trigger D flip flop. Okay. So this we discussed. So for this I am writing the code. So here if you see, this is divided by 5 circuit with 50% duty cycle. So module divided by 5 circuit, 50 DC, input clock, input reset, output Y. I need to declare, so I need to declare how many flip flops I need to use, 3 flip flops, 3 flip flops, range 2 down to 0, count, and internal registers I need to declare, range Q1 and Q2, and I need to design modify counter. So modify counter means it will count from 0 to 4. Again, it will roll over to 0. Always at the rate passage of clock or passage of reset begin. If reset, count will be become 0 and Q1 becomes 0. Else begin. If count becomes 4, again count should become 0. Otherwise, it should do normal count. Okay, this is the code for what counter. Okay. So next, this is the code for counter, and I need to design the code for negative edge trigger D flip flop. Okay, so negative edge trigger D flip flop, that is always at the rate negate of clock or passage of reset begin. If reset Q2 equal to 1 tick binary 0, else Q2 equal to Q1. And at last, what I need to do? I need to do operation of Q1 and Q2. Assign Y equal to Q1 or Q2. Okay. So this is divided by 5 circuit. Is it fine? Test bench is same only. Okay. 5 steps are there. And this is Mod 7 counter. So here you are taking Q2 only. So I design the Mod 7 counter. So this is the Mod 7 counter. Mod 7 frequency divider Mod 7. So this is the frequency divider Mod 7 counter. So first module name is frequency divided by 750 DC. Input clock and reset I am declaring, and output clock underscore out. So reg 2 down to 0 count, and reg Q2 delayed. Okay, this is Q2 delayed. First I am designing Mod 7 counter. It should count from where to where? 0 to 6. Always at the rate passage of clock or passage of reset begin. If reset count equal to 0, else begin. If count equal to 3 tick decimal 6, count becomes 0, else normally it should count. Okay. So this is the code for counter. Okay. Next I need to design negative edge trigger D flip flop. So always at the rate negate of clock or passage of reset begin. If reset equal to 1, Q2 delayed I am making to 0. Otherwise Q2 delayed is non-blocking with count of 2. Okay, count of 2 I need to give. Okay. D flip-flop is normally it's a sequential buffer, no? Whatever the input is there, you're getting. And assign clock out equal to what? You need to do the R operation. You need to do the R operation. Then you are getting clock out. That is the output. End module. Okay. Test bench is same. This is frequency divided by 7. And even also we already seen for events from frequency divided by 2 circuit, any extra circuit is required. Extra circuit is not required, no. This is on for this is off for uh, even, yeah. So that means F by 2 circuit directly. First I told you the F by 2 circuit. Okay. Extra circuitry is not required. First this the one I told you, no. This is a frequency divided by 2 circuit only. Okay. And if you see the F by 4 circuit, F by 4 circuit, F by 4 circuit, any extra circuit is required. Yeah, off for 2 cycles and on for 2 cycles. So you are achieving 50% duty cycle. Okay. So 50% duty cycle. F by 4 circuit also I wrote the F by 4 circuit frequency divided by 4 circuit. So this is frequency divided by 4 circuit. So module frequency divided by 4 circuit 50% duty cycle. Input clock in clock underscore in input reset. I am declaring output clock underscore out. I am declaring range 1 down to 0 count. Uh, so first that means I need to design mod for counter, no? Mod for so assign clock out equal to clock count 1 always at the rate passage of clock or passage of reset begin if reset count equal to 0 or otherwise end else begin count equal to count plus 1. Okay, end module. So I'm designing mod for counter here. So that means cycle will repeat from 0 0 0 1 1 0 1 1 again it will roll over to 0 0. Okay, so just I'm designing the mod for counter only. Okay, so frequency divided by 4 means what? Mod 4 counter only. Okay. Is this fine? Any doubts or queries? Okay. This is divided by 4 circuit. And next we have seen F by 6 circuit. So F by 6 circuit, this is off for 4 cycles. This is on for 2 cycles. Passage, no? We need to alter the out passage D flip flop. We need. Okay. So I wrote for F by 6 circuit also. So this is a basic circuit, basic circuit. So input clock, input reset, output F6 underscore out, reg 2 down to 0 count, reg Q3, wire Q3. So first I need to design which counter? Mod 6 counter. Okay. Always generate passage of clock or passage of reset. Begin if reset. So count is initialized to what? Three tick binary 0 0 0. Else if count becomes 5 means count should come to 0. Else count will be count plus 1. Okay. Again Q2 is the MSB of the counter. No. Actually what is Q2? Q2 is the MSB of the counter. No. So Q2 I need to initialize to what? Count 2. Okay, count 2 is there. That is given to Q2, and I need to develop the positive edge trigger D flip flop. Always at the rate passage of clock or passage of reset begin if reset. If reset equal to 1, Q3 is equal to 0, else Q3 equal to Q2. Okay, and at last what you need to do? You need to do the R operation. That is Q2 and Q3. That is by using assign statement. Assign F6 of underscore out equal to Q2 or Q3. Okay, end module. So this is about the frequency divider circuits. Any doubts or queries? So next tomorrow we'll see the state diagrams. Hmm? Yeah, yeah, okay, fine, fine.